Let's try to solve this problem here. So you have a vessel containing hydrogen gas of 2.20 times 10 to the power of 18 molecules per meter cube, and the mean square speed of the molecules is 4.50 km per second. Okay, I think this question there's a bit of problem. They shouldn't call this as mean square speed. They should call it as root mean square speed. I think they miss out a root over here. Okay, but the rest thing should be fine. Okay, so a vessel containing hydrogen gas of 2.20 times 10 to the power of 18 molecules per meter cube. Again, you see there's number of molecules. This is a number of molecules. You might think of it as being n, but no, you can see there's a per meter cube behind. So what they're trying to say is, if you happens to have a volume of 1 meter cube, if this is a volume of 1 meter cube, you'll find that inside there's a lot of gas particles, but if you count the number of gas particles that are inside this volume, you'll find that there will be 2.20 times 10 to the power of 18 molecules. Does it mean that your volume of your container is 1 meter cube? No, your volume can be smaller than that, your volume can be bigger than that. But if you focus on the space which has a size of 1 meter cube, you'll find this amount of molecules inside it. But does it mean that it's 1 meter cube? No. It can be greater, it can be smaller. But if you focus on that particular volume, you'll find inside there to be, on average, having this amount of molecules inside it. Okay, so what I'm trying to say here, okay, I'm maybe complicating things over here. But actually what this value means here is N over V. Okay, so N over V is equals to 2.20 times 10 to the power of 18 molecules per meter cube. Meter negative 3. Okay, so that's the number of molecules that you can find for every 1 meter cube of volume you have. Okay, the root mean square speed of the molecules is 4.50 km per second. So root mean square speed, that is VRMS, is equals to 4.50 km per second. So again, it's something that needs to be converted. So let's do the conversion right now. You leave the km on top, it's per second, you bring it to the bottom. Second, don't need to change, or you only need to change the km to meter. So you eliminate km by putting it on the opposite side of the fraction. Then you put meter over here. So 1 km is equivalent to 1000 meters. So from here, you are finding that it's equivalent to 4500 meters per second. So that's the root mean square speed of the molecules at temperature of 50 degrees Celsius. Again, temperature, you are not allowed to operate in degrees Celsius. You have to change that degree Celsius to be in the unit of Kelvin. So 50 plus 273.15, you get the unit to be in Kelvin. So that's 323.15 Kelvin. Okay, so you have converted everything clearly. So know what information you have here based on the rectangle. Okay, let's draw a rectangle again. Based on a rectangle, you have P, you have KTR, you have temperature, you have VRMS. So the information that you have right now, it's the VRMS and the temperature, which is around here. VRMS and the temperature. So these are the things that you have already. Next, they ask you to determine the pressure of the hydrogen gas. So pressure of the hydrogen gas is this side over here. So you are going to use this side of the rectangle over here. You are going to focus on this side of the rectangle, which have two equations. One is PV is equals to 1 over 3 Nm VRMS square. Another one will be P is equals to 1 over 3 rho VRMS square. I believe we don't have the density of gas over here. What you have is the number of molecules per unit volume. You need to bring the volume to the right hand side. So we are going to pick the top equation here for question A. So for question A, PV is equals to 1 over 3 number of molecules, mass of one molecule, VRMS square. So bring the volume to the other side. You have 1 over 3 number of molecules per unit volume, mass, VRMS square. Okay, so now in this arrangement, I believe you have all the necessary values. Oh, you don't have all the necessary values. Let's continue first. You don't have all the values actually. The number of molecules per unit volume is 2.20 times 10 to the power 18. But the problem is you don't have the mass of one single molecule. What you have here is the molar mass of hydrogen gas. So the molar mass of hydrogen gas is capital M and is 2.02 gram per mole. Again, we are going to convert it. So 2.02 gram, leave it on top, per mole, bring it bottom. Okay, you are going to eliminate gram, introduce kg. So 1 kg is 1000 gram. So that will be 2.02 times 10 to the power of negative 3 kg per mole. Okay, but we know that molar mass can actually help us to determine the mass of one single molecule. Okay, if you think about it, the molar mass is the mass of 1 mole of gas. So 1 mole of gas, how many molecules you have? You have the Avogadro number of molecules. Okay, Avogadro number of molecules multiplied by the mass of every single molecule, you get the molar mass. Okay, so through this simple manipulation here, you are able to determine the mass of one single molecule. So 6.02 times 10 to the power of 23, then you get your mass of one molecule. So you can put it as a fraction, so it will be 2.02 times 10 to the power negative 3 divided by 6.02 times 10 to the power of 23. So this is the mass of one single molecule. Again, molar mass is defined as the mass of 1 mole of gas. So 1 mole of gas has how many molecules inside? Has Avogadro number of molecules inside. You know that each molecule has a mass of m, so if you multiply it, you get the molar mass back. So through this manipulation, you get the mass of one single molecule to be this fraction over here. So you can put it in 2.02 times 10 to the power of negative 3 divided by 6.02 times 10 to the power of 23. So that's the mass of one single molecule. Now multiply by VRMS square. VRMS square, you already obtained the VRMS 4500 and you're going to square it. Okay, you square it. And from here, if you do your calculation, you get your pressure to be equal to 0.0498 Pascal. Okay, so that's how you obtain the pressure of the hydrogen gas. So once you obtain the pressure of the hydrogen gas, you can proceed to the next question, which is to find the average translational. Again, we are restricted to translation only. Translational kinetic energy of a molecule means you're going to focus on one particular molecule only. You're not going to look at the whole gas system, just one single hydrogen gas molecule only. Again, you're focused on translation, so you don't need to take into account the rotation. So how many degrees of freedom do you have? You have 3 degrees of freedom for translation. So 3 degrees of freedom for translation. How do you determine the average translational kinetic energy of a molecule? I will need a new page to do this. So average translational kinetic energy, well, we are restricted to translation, so KTR of a single gas molecule. So it's not the whole gas system, we do need to write total. Okay, so for this question, we know that it's 3 degrees of freedom for translation. Each degree of freedom, you have half kT of energy based on principle of equipartition of energy. Okay, so it's 3 over 2 kT. So 3 over 2 K is 1.38 times 10 to the power negative 23. Then you have your temperature being given in the question, and we already convert it into Kelvin. That's 323.15 Kelvin. So from here, you can determine the KTR, the translational kinetic energy will be equals to 6.689 times 10 to the power of negative 21 joule. Okay, so that's the average translational kinetic energy of a molecule of hydrogen gas. Okay, then we can proceed to determine the internal energy of the system if the vessel has a volume of 2 liters. Okay, now they are going to specify what's the volume. Okay, well, there's a reason behind it, but I'll need a new page to explain it. Okay, so now they're asking for internal energy of the system. We know that internal energy of the system is represented by symbol U and is equivalent to the total kinetic energy that we have in the system. Why there's no potential energy involved? Because we are going to neglect all the intermolecular forces in between the molecules. So it's just kinetic energy total only. Okay, you know that there are 3 different versions of this equation for K total, but we have to be very clear what's the degree of freedom first. So let's change it into degree of freedom, F over 2 nRT. Okay, the degree of freedom, we have to look at what type of gas is this. This is a hydrogen gas. And we know that hydrogen gas is H2 and it exists as a H and another H together. So this is diatomic. So if it's diatomic, the degree of freedom, including rotation, will be equals to 5. It's 3 plus 2 equals to 5. So it's 5 over 2 nRT. Okay, but if you are getting excited wanting to do your substitution right now, you'll notice that you have the temperature, you have the gas constant. The problem is you don't have the number of mole here actually. If you don't have the number of mole, then it will get a bit difficult for you to do this substitution over here. But you know from your ideal gas equation that PV is equals to nRT. So what actually you can do is you can change this nRT over here to be in PV right now. So you have your volume is 2 liter, you have to convert into per meter cube. You have your pressure is from question A, and you already determined the pressure to be 0.0498, so the rest is just substitution. Okay, 5 over 2, pressure is from question 2, right here, 5 over 2. Pressure is from question A is 0.0498, that's your pressure. For volume, the volume given is 2 liter, we have to change it into meter cube. If you refer to my notes, I already mentioned that liter and meter cube, the relationship is 1 meter cube consists of 1000 liter inside it. Okay, so it will be 2 times 10 to the power of negative 3 meter cube. Okay, so if you substitute in 2 times 10 to the power negative 3 inside, then from there you're able to get your internal energy, which is equals to 2.49 times 10 to the power of negative 4 joule. So this will be the internal energy of the system if the system happens to have a volume of 2 liter. Of course, if you change the volume, then the internal energy will be different. Okay, so this is how you manipulate this rectangle over here to obtain different quantities over here. At the same time, be very clear with what they are asking for. Either it's for a single molecule or it's for the whole gas system. What type of energy, does it include translation, does it include rotation or does not include rotation. All these things through practice, you're able to be familiar with it, and you're able to choose the correct equation to determine the value required by the question.